So I just want to say up front, the lecture is about attosecond science and technology most generally. So of course, if you are no expert, that's the field where we are going to dive in. So I'm going to teach you a little bit about the principles of the generation of these extremely short light pulses and try also to guide you into the challenges of this technology and applications. But in terms of applications, I would concentrate on, that's why I have this title here, on using this technology to really trace or image the electron dynamics in matter, and more specifically in molecules. That's more I would say, the core business of my group, to establish a new field which we called attosecond chemistry, with the purpose of really exploiting this technology to control the chemistry at the extreme or the fastest timescales. Just as a very quick overview about the place where I'm working at, I mean, it was mentioned, I am part of DAISY and the Center for Free Electron Laser Science in Hamburg. Here you see an aerial picture, and this is that you see here is actually the synchrotron. It's a very big facility producing X-ray pulses. My labs are in fact located in the synchrotron in the Petra Hall here, more or less. Not because we use the synchrotron light, but we use the stability of the floor of the synchrotron, which is a big concrete slab, because our interferometers, as you will see, they require attosecond stability, which means nanometric stability. And that's the best place in the world where to place your very sensitive interferometer in a synchrotron. But yeah, we have laser-based laboratories. Here you see some pictures of people working on the ultrafast lasers, a lot of colors and vacuum chambers. I will show you why. And here is a picture of the group in Hamburg. In Hamburg, we also have some sunshine sometimes. And we have group outings. If you want to know more about the group, you can visit our website. And of course, you can contact me anytime to reach out or have more information. So let me start from, first of all, the very basic principle of ultrafast science. So why are we interested at all in producing very short light pulses? Of course, there are many, many reasons, but I would focus over the dynamics of matter. So most of the matter, as you studied it during your studies, is exposed to external stimuli. And this means that matter is far from being static. Of course, there are cases in which matter is static, but most of the cases, matter is in a out of equilibrium state, which means that the external stimuli has driven matter to do something, to have some functionality. And that's why I would say it's very important to look into which kind of excitation has happened in matter. And more specifically, we are looking into the energy scale as physicists. So which kind of energy excitation has happened into the system in matter. So if the energy scale is in the order of a fraction of an electron volt, we're talking about milli-electron volt. Often this is the thermal energy scale of the excitation. That it's quite often the case in condensed matter systems. Then the dynamics is more of a structural dynamics. This means that the structure of matter can change, and there you have phonons, vibrations. So matter is starting to move a little bit, and this means that the atomic nuclei that compose matter are displaced, so to say. This dynamics, this structural dynamics, is happening in this energy scale. And as physicists, you know, energy means time. I mean, there is a very strong relation between energy and time, and this milli-eV scale corresponds to picosecond typically, or 10 to the minus 12 seconds. Of course, it could be even slightly faster. It could be femtoseconds, so down to 10 to the minus 15 seconds. And that's the time it takes typically for a structure to rearrange or to move, okay? Now, if we go to higher energy scales, if our stimuli, our external stimuli, for instance, let's consider light. Light could be energetic. You can go at the electron volt level, okay? for instance, in the visible light, or even kiloelectron volt if you consider an X-ray excitation of matter. Okay, you deposit a lot of energy in the system. Now, this energy is a lot, and it typically is electronically exciting your system, and electron starts to move really, really fast, or redistribute very fast in matter. And since we are talking about this energy scale, then we are talking also about faster time scales, from femtoseconds, 10 to the minus 15, to attosecond, which is 10 to the minus 18 seconds, which is an extremely small fraction of a second. It's an extremely fast dynamics. I generally say it's wrong to say that electron dynamics occur at attosecond time scales. You may have heard this, especially after the Nobel Prize in Physics, that we heard there was a lot of general advertisement. Yes, that's the time scale at which electron moves. No, it depends on the energy scale of the excitation. If the excitation happens at the milli-electron volt scale, also of electronic excitation, electrons move very slow. In fact, even at femtosecond or picosecond time scales. But if the excitation occurs at these very high energies, then we are talking about very fast dynamics. And that's very interesting for everything that concerns with the light harvesting. When you want to harvest the energy coming from those photons and get some functionality out of matter, you need to work at these time energy scales. Okay, that's the main motivation. So we are, of course, if you would zoom even more in matter, you go to even high excitation. We're talking about high energy physics, nuclear physics. There you're looking more into the nucleonic motion. So if we would be able to produce in future light pulses that can access even those ultrafast dynamics down to the zeptosecond time scales, we will even look deeper in matter into the nucleonic motion. But for now, we are stuck, or we are interested into this time energy range, which is, say, again, electronic motion connected with those energy excitations that really motivate us to improve our understanding about these dynamics of matter for better light harvesting mechanisms. Okay, now what can we do here? So I just have, of course, again, try to zoom into the molecular dynamics, because that's the topic that we will see the most today. And I'm trying to look into what can you effectively do with light in molecules, right? And something that you can do is that you can, again, excite your molecule with light, which can be the sunlight, could be laser light, and activate a certain structural rearrangement. So again, nuclei moving, the structure of the molecule changes. You may have heard about photo switches. These are molecules that switch. It's like really a click, and as they switch, they enable something. They enable vision. They enable light conversion and energy storage. So that's a very important process in chemistry and in light harvesting. And this happens, as I said, in femtosecond to picosecond time scales. And this is the time that you need to, or so to say, the time scale that you need to explore to ultimately have a sort of a control over these dynamics, which is the domain of, so far, femtochemistry. When we have got, the possibility to access faster dynamics, then, as I said, we can start to look into how the electron density distributions, or the electrons, rearrange in molecular systems. Often this happens very fast. So electrons that here are represented like these colored bubbles that you will see later also in my presentation are changing their position in the molecule very rapidly. And you know, electrons are in fact the glue that keeps the atomic nuclei together in molecules. The electrons that are distributing in specific ways are determining the forces that are driving the atomic nuclei in the molecular reactivity. So the fact that the electrons move from one side, from one functional group to another of the molecule, can change drastically the activity of the molecule. So the goal here of attochemistry is to figure out whether we can achieve a certain level of control over this ultra-fast electronic redistribution, such that we can, in principle, also even redefining the concept of a bond, in a sense, because we can really drive electrons into specific places and control the reactivity of the systems. How can we access these extremely fast dynamics? How can we really catch dynamics that is that fast? Well, we do it exactly with the same principle of flash photography. So this is what you have seen probably multiple times in different ways. I mean, this is the problem of the revolving cat, how a cat is always landing on his feet. That can only be seen if you have these very fast flashes of light shining a dynamical object, in this case, a falling cat. Why the light needs to be fast? Well, because typically our detectors are extremely slow for the dynamics we want to measure in certain cases. And if the detector is slow, then of course, if you have continuous illumination, you will average all possible position of your object along the dynamics. So you're kind of blurring the dynamics. You cannot see it. Same happens with your eyes. We have wonderful detectors here, but they are not fast enough to see, for instance, the motion of the wings of the hummingbirds, right? I mean, we just see an average position of the wings or the raindrop falling on the floor. We always average all possible positions because our eyes are not fast enough, and so you see only, I would say, a blurred dynamics. The trick of flash photography is very simple. Your detector is slow, and it's constantly acquiring. But if you illuminate the object with a very short flash of light, then the detector can acquire something only when the light is there, right? And in the meantime, your object is changing positions. So the fact that the light is short enough compared to the dynamics that you're measuring enables you to see the various position in time. So that's the example that I like the most to show how ultrafast science works. It's really, we need ultra-short light pulses of the same duration or comparable duration compared to the dynamics we want to measure to be able to do exactly what flash photography is doing in this case. Okay, so but how can we effectively do it? I mean, how can we record the dynamics of matter? So we're not talking about a cat moving, of course. We are talking about electrons and atoms and so on and so forth. And so how can we do that? So in ultrafast science, and we will see now very soon about the short light sources, so how to create these short flashes of light. But for a moment, let's consider we have those available, okay? So we have these very short flashes of light. How can we record the revolving cat in the electron dynamics world, so to say? We have to do it with a method that is called a pump and probe, which is the typical approach in the time result measurement. So you use basically light, and for instance, I'm just making a very simple example here. So if you would have light going through your sample that you want to investigate, then you will typically position the detector after your sample. You look at the light which is absorbed by your sample. There is a very simple law here, the Beer law for the absorption of light, that it will show you, okay, light has been absorbed, so there is matter there, and it's interacting with light and is absorbing light. This is a static measurement, so will not give you any information about the dynamics which is happening in matter. So we need a first pulse. We need a first pulse which is exciting these dynamics. That's the light, that's the stimuli which is exciting matter, so it's initiating a certain dynamics. And this is the pump. It's also the trigger, what tells you what is the zero time, okay? Because you need an absolute reference. And then, like I said, the probe, which is now a second pulse. And I will look now at the transmission, and this is what I detect with my detector as a function of the delay between the two pulses. And this is the flash of light, which is acting as the flash photography. So there is a fast dynamics happening here in the sample. And this probe will look at these dynamics at different time delays with respect to the pump. And if you look now at the absorption, you will see that the absorption is transiently changing of light in time with the time delay between the two pulses. And you can extract information from these dynamics that is recorded. So it's really like filming what's going on in matter using these pump and probe pulses. I told you already that it's important that the flash of light, especially both the pump and the probe, but especially the probe, you want to have it very short to see, the dynamics, not to have not this blurred image of what's happening in matter. And therefore, there has been a very strong link between what we have been able to observe in matter in terms of physical phenomena, and the laser technology, because depending on the duration of these light pulses, these extremely short light pulses available out of our laser box, we have been limited only to a certain number of phenomena. Especially here, you can see a diagram in which the major discoveries or the major improvements into the laser technology has happened. You see that we went from microsecond pulse durations in laser technology in the 60s down to few femtosecond laser technology here around year 2000. Well, a little bit before the year 2000. And this actually has been improved. I will not, this is not a lecture about laser technology, so I will not dig into the laser technology itself. But indeed, the laser technology enabled faster and faster processes to be studied until we reached the so-called femtosecond barrier. You see that the graph is flattening, right? I mean, there's been a tremendous progress, and then at some point we were stuck with femtoseconds. And I said, femtoseconds is primarily structural dynamics, but if you want to look into these ultrafast electronic rearrangements, at high energy scales, this requires attosecond, or well, 1 femtosecond, 2 femtoseconds, or attoseconds. And this is something that we were kind of not reaching yet. And there is a fundamental limit of how short your pulse can be, and this is related to the so-called carrier wavelength, so the main frequency, the color of your light. Because the light needs to have at least one period, right? And if the period is longer than 1 femtosecond, you cannot have attoseconds. It's intrinsic limit. And therefore, given the wavelength at which these laser sources were lasing, there was no possibility to lase with pulses shorter than a femtosecond or a few femtoseconds, okay? So that was the fundamental limit until a very new discovery has been done. I mean, the discovery was before year 2000 on an extremely nonlinear process that we will see shortly, called high-order harmonic generation. That's the process that has been awarded the discovery that's been awarded the Nobel Prize in Physics a few years ago to Pierre Agostini, Ferenc Krauss, and Al Ludier. It's really for the development of this technology that ultimately enabled to access the attosecond domain. And we had to do something that we will see soon to the lasers in order to access this regime. And nowadays, actually, this point is not up to date. I have it up to date. Actually, we go down to even 19 attoseconds. That's the fastest source available at the moment. After this introduction, I just want to tell you what I'm going to talk about. So at the beginning, I'm going to explain a little bit about the attosecond pulse generation process, so how these extremely short pulses, the shortest pulses available as of now, are generated. Then I will talk a little bit about the implementation of so-called attosecond chronoscopy approach. This is the way we do the pump and probe that I explained you before. So how can we clock? How can we measure the electron dynamics? And we'll see how far we manage to go with the attochemistry, so with implementing those techniques to study the dynamics in molecular systems. So let me start with the generation. So I told you already that the fact of having very short pulses, or the duration, the shortest pulse duration, is limited by the carrier wavelength or the color of light. Okay, so again, depending on the wavelength at which the laser is lasing, we can reach a limited, so a limit in terms of pulse duration, which is dictated by the period of the light. Okay, so one first trick could be to say, okay, if I have a laser which is operating in the infrared or around these colors, then I can do frequency conversion, which is a process that enables, exactly like as the guitar that I'm showing here, to generate harmonics of the fundamental frequency, which is your laser frequency. And this happens when you have a perturbative nonlinear interaction between light and matter. So a perturbative interaction means that the laser is not that intense. So you have a mild perturbation of your system of matter, and this mild perturbation makes the electron oscillating also a little bit faster compared to the laser frequency, such that I can produce harmonics for non-centrosymmetric media, the second harmonic or even the third harmonic. And basically, you see here the law of perturbative nonlinear optics, that the polarization in the medium induced by the laser is proportional for the second harmonic to the square of the electric field of the laser, for the third harmonic to the third power of the electric laser, and so on and so forth, okay? Fantastic. So I can produce harmonics, and already by doing the harmonics and get into shorter wavelength, I can shorten a little bit the pulse duration, okay? That's a lot around this generation of short pulses that I don't have the time to go through, but ideally the idea is I have to get the wavelength shorter and shorter. But there is a limit, because as you increase the order of the harmonics, the efficiency of the generation of these harmonics drops exponentially. So actually you don't get efficient high order harmonic generation with the mild perturbation of the medium. In order to really shift the carrier wavelength to very high photon energies, here we are talking about extreme ultraviolet light or even soft X-ray light in some cases. We really need an intense interaction between the laser and the matter, such that we are talking about extreme nonlinear optics. In this scenario, you need a laser which is focused, we say, above 10 to the 13 watt per square centimeters. So we have a lot of energy concentrated in a very small volume. And we interact, for instance, let's take a gas, a Nobel gas, the simplest case. So we have these intense femtosecond laser pulses focused on the gas target. If this is happening, if we enter this regime above those intensities, we start observing high order harmonics of the fundamental laser that are, I would say, odd orders of the fundamental frequency of the laser. Now, this phenomena has been observed at first by around 1987, 1988 by two groups, one in the US and one in France, this one being the group of Anne Lullier. And this was because there were, I mean, before I was asked as a scientist, are you excited more when you have a big discovery or when you have a lot of small discoveries? Or are you excited by proving theory or by discovering something completely unexpected? I would say a scientist has to be excited by something unexpected. And this was totally unexpected, okay? Not predicted theoretically and completely not expected from the physics that we knew at that time. And that was very exciting. So we're having these very intense lasers for the first time available. And so they said, oh, fantastic, let's focus them very hardly on a medium to explore fluorescence. They were looking into atomic fluorescence, a completely different process. And instead of collecting the fluorescence, they were collecting a new radiation generated, which was indeed showing very high order harmonics. So you see here, this is the harmonic order that you have here on this axis. You see up to the 35th order, so very high order harmonics. And as you see here, actually, this is the first are the third, the fifth, the seventh harmonic. Here we are still in the perturbative nonlinear optic regime. You see that there is this decrease, exponential decrease of the signal. So you would expect the signal here to go exponentially to 0. And instead you see a plateau appearing with a lot of harmonics of the same intensity, and then a cutoff. Of course, this is not, there is no lunch for free, so at some point the process is ending, so we don't generate radiation up to the kilo-electron volt, unfortunately. But still, there are a lot of harmonics here, and they were wondering, why are these harmonics there? I mean, there's nothing, I mean, it's actually not following at all what we would expect with the perturbative nonlinear optics. It took a little bit of time to work out what's going on. That was basically proposed at first by Ken Schaefer, and then Paul Corkum came up with this very nice three-step model, which is a semi-classical model, which can be explained to high school kids. I mean, it's really a simple model to be understood from the physics perspective. I really like it a lot. Here, you don't need to solve the Schrödinger equation to understand what's happening in the light-matter interaction. You just need classical physics and a little bit of quantum mechanics, but not that much. In fact, the process can be explained in these three steps, in which the only quantum mechanical step is the first one, and it's called tunnel ionization, What happens is that your electron is trapped in a Coulombic potential. So this is your atom within I mean, for simplicity, let's consider the hydrogen atom with one electron trapped in the Coulombic potential. Your laser comes, and what happens is that the laser intensity is such, I mean, the laser is so intense that the Coulombic potential is deflected. It's actually bending, right? And it's bending in a way that for the electron is so easy to tunnel out now. So the electron is no longer trapped in the Coulombic potential. It can tunnel out, and now we have an electron available in the continuum. And this electron is available, and it doesn't care anymore about the parent atom, okay? It's completely free. But there is a laser there. There is a laser which is oscillating back and forth because light is oscillating. So the electron is accelerated according to Coulombic force. So this is like physics, basic physics, electromagnetism, classical physics. The electron is accelerated away from the parent ion and then is driven back by the laser until it reaches again the parent ion, and there is a probability for the electron to recombine, and that's the third step. It recombines, but the electron has accumulated so much energy because it has been accelerated, driven back, it recombines, and it has to release all this excess of energy. And this excess of energy is released in a radiative way with the emission of this photon. Now, this process is actually happening every half cycle of the driving laser. So you see here is a schematic in which you have ionization, acceleration, and recombination, and you emit these blue pulses. So the red one is the femtosecond driving laser, at which the atom is exposed, and the blue one is the pulse emitted. Every half cycle, you emit a pulse, okay? And so you end up with a train of very short pulses because this process now is happening within a fraction of a cycle of an optical laser. So the optical laser is oscillating with a femtosecond periodicity, but you're just generating in a very small fraction of it, which is typically hundreds or tens of attoseconds duration of light. And you have a train. So you have a comb of attosecond pulses, which are separated of half of the periodicity of your laser. So the problem is completely centrosymmetric. So it happens on the one side and on the other side of the atom all the time, okay? Now, if you have a comb of pulses in the time domain, you know, mathematically this corresponds to a comb of frequencies in the frequencies domain. So a comb is always a comb according to Fourier transformation. And so you get these odd order harmonics of the fundamental that are separated by twice of the driving laser frequency. This is a sort of a quantum interference because every pulse is coherently emitted by your laser, and they are phase locked, and they have a phase difference which is due to this half cycle of the laser. And so this light interferes, and out of this interference is creating this comb of frequencies. And that's the nature of this, the origin of this process with all the comb of harmonics. Just to analyze a little bit better the spectrum, you have this comb of odd order harmonics with a cutoff. And if we analyze, the cutoff is due to the maximum energy that the electron can acquire in the continuum with this trajectory that I explained before. And there is a limit amount of energy, which is the sum of the kinetic energy acquired by the electron, this first term, and the binding energy of the atom that is released when it recombines. Now, the interesting thing that I want to tell you here is just that, okay, you would say, what can I do with my laser to push this cutoff as far as possible in the high photon energy? Because I want to emit high energy photons, and I want to emit, so to say, emit them the most efficiently. Well, you can do multiple things. Since this cutoff position depends on the ponderomotive energy or the kinetic energy, and this ponderomotive energy is proportional to the intensity of the laser and to the square of the driving wavelength, then you can either increase the intensity of your laser, or you can increase the wavelength at which you drive the harmonic generation process, and you get far you push the cutoff far in the high photon energy region. As I said, nowadays we can reach very high photon energies. Here there's the central photon energy of your spectrum in the harmonic generation process. It can be even around 200 or 300 electron volts. which is a very high photon energy. So remember, we start with an infrared laser, which is approximately 1 electron volt, and we emit radiation at 200 or 300 electron volts. So it's a massive amount of photon energy gained in the process, which is quite impressive. And even the pulse energy, so how much energy can you get out of these XUV lasers or soft X-ray lasers if you want? This is coherent radiation. It has all the properties of a laser, right? So it's really lasing like a laser. It's directional. Okay, in this case, it's polychromatic because it's very broadband. It contains these odd order harmonics, but it has a very confined propagation like a laser. It's coherent, and it has also relatively high pulse energy in a sense that nowadays sources can even approach the microjoule level, which is a very good performance for an attosecond light source. And it's a tabletop source, so you don't need a synchrotron like I showed you before, or a free electron laser, a massive machine to emit radiation in the soft X-ray spectral region, so up to 500 electron volts even. You just need an optical table with the laser and some vacuum chambers where to make the high-order harmonic generation process. Something that I neglected to mention so far is the macroscopic property of this process. So typically, you don't generate harmonics in a single atom. You don't have one atom and you generate the radiation, because that you would not be even able to detect. In a lab, you will put your gas, for instance, atomic gas, and you generate from multiple atomic centers. So what happens is, like in this picture, you have multiple atoms, and then you have your laser field, and every atom is emitting some of these, this XUV radiation, right? This XUV field. And what you want is that these waves are actually adding up in phase, right? Because otherwise there would be a destructive interference, and you can even basically kill all your radiation. You want all the radiation to oscillate in phase and to adapt coherently in order to get the maximum photon flux out of your source. And this is called phase matching. For the few experts of you that have been working in nonlinear optics, they know the key ingredient to generate harmonics is always to phase match the radiation, or to phase match the nonlinear optical process. And phase matching has to be considered also for the high harmonic generation process, with multiple terms that I will not go into the details. But if you look into this phase matching, a key thing is emerging out of the phase matching, and it is called the critical phase matching regime. So in the critical phase matching regime, in order to balance all these terms that depends on the neutral gas population and the ionized fraction of the atoms, you need to limit the amount of ionization that you have in your medium. And this means that you have to limit the intensity of your laser. Before I told you, you can extend the cutoff indefinitely with the laser intensity, but if you increase too much the laser intensity, you ionize completely your medium, and this will completely destroy your phase matching. So you will not produce radiation anymore. You will not detect photons. And so you have to stay below the critical phase matching, limit the laser intensity, and so limit the cutoff that you can reach. There is another approach that we also been recently investigating with my group, which is called the overdriven regime, where instead you overdrive the process, you go to extremely high intensities, even 10 to the 16 watt over square centimeters, and you use reshaping of the driving field, which is happening while propagating in the medium. The driving field gets very distorted, and this is changing the phase matching in a way that you can extend a lot the cutoff. And this is just an example in which I show you some harmonics that we have generated in this overdriven regime in our lab. Even with short wavelength, we reach up to 250 electron volts. So we managed to phase match a very long cutoff. Or with longer wavelengths, we cover the full water window, where the water window means the region, the photon energy region, where water is transparent, but you have the absorption of the main atomic species that are contained in organic molecules like carbon, nitrogen, or oxygen. They are the fingerprinting, so they will absorb the radiation. You will see you have them on target but the water will let the radiation through. And so you can study, for instance, in this water window, molecules that are solvated in water that otherwise with the visible radiation you would not recognize in your target. Let me go back for a moment to the attosecond pulse generation process, because I so far told you I want to generate the shortest pulses in the world, the attosecond pulses, and you can tell me, yes, you did it, but you did a train of attosecond pulses. At the end of the day, you have a train of a lot of attosecond pulses, but this train, the envelope here is still a femtosecond pulse. No, I mean, I haven't shortened so much my resolution. You remember the flashes of light that I told you before. I want a single flash, a single attosecond pulse. And so I need to apply a trick here. And the trick is to gate the higher order harmonic generation process. So imagine now you switch off with some magic trick the higher order harmonic generation process for some of the recollision events. So for instance, here, this pulse, and this pulse are suppressed. So here the field cannot generate harmonics. You switch it on only for half a cycle of the laser field, and then you switch it off again. And if you do that, you confine the harmonic generation only in a single event, right? And you have a single pulse out of this train. If you have a single pulse, then a single pulse has to correspond to a continuous emission because there is no interference anymore. So you don't have the harmonics anymore. What you have is a broad continuous emission, like this spectrum here, completely continuum, and this corresponds to a single attosecond pulse. Okay? When I say broad continuous emission, this emission can cover several tens or several hundreds of electron volts now. Okay, so I think there is no other source in the world with such a coherence and broad coverage at this wavelength. It's extremely broad. No laser will laze with this bandwidth coverage. And that's also what enables the shorter light pulses to be generated, because again, the Fourier transform is connecting a broad spectrum to a very narrow pulse, to a delta pulse. So we need really a very broad emission to get this very short pulse in time. Okay. I want now to show you a little bit how to characterize those pulses and how we can do this pump and probe, this kind of measurement, this stopwatch measurement that I told you before with such short pulses. And for that, I'm going to talk about attosecond chronoscopy. You will see in a moment why I say of photoemission. Because that's one of the problems that have been really tackled and investigated and studying in depth using attosecond technology so far. So there are basically, you would say, I should do pump and probe, and then you would say, okay, now I have these attosecond pulses. Can I just split my beam in two, and then I use one as the pump and one as the probe? This has a little bit of a drawback. I mean, first of all, this extremely nonlinear optical process is highly inefficient. So it has a very low conversion efficiency. And so if you split your photons now, if you use half of the beam to pump and half of the beam to probe, you don't have enough pulse energy to really see something in matter. There are some setups nowadays that are doing this approach, but this is not the most common way of performing attosecond time resolved experiments. The most common way is to build an interferometer. I remember I told you we really need super stable interferometers. In an interferometer, you always split your beam in two arms. And in this case, this is your incoming laser, femtosecond laser, and you split it in two arms. In one arm, you will generate the harmonics in the gas cell via the high-order harmonic generation process, and you generate this extreme ultraviolet radiation. And in the other arm, you take a small portion of your laser, you use a delay stage to change the delay between the two pulses, and then you bring it back together with your attosecond pulse. It has the advantage that now you say, okay, now I still have a femtosecond pulse together with an attosecond XUV pulse. I'll see, it might be not optimal, but in many cases, this is actually working very nicely. And it's working nicely because the two pulses are coherently coherent to each other. I mean, remember, this laser is still the laser I use, the infrared laser is still the same laser I use to produce this XUV radiation. So these two light pulses are phase locked. They know each other very well. They're not randomly combined light sources. They are very coherent and phase locked. And this is enabling a number of interferometric experiments that are extremely challenging, but at the same time providing you the finest temporal precision in ever clock, time resolved measurement with the clock that is given by these attosecond pulses. What you can do after is you have this nice combination of pulses, you interact with your sample. The sample can be a gas, can be a solid, can be a liquid, depending on what you're interested to investigate. And then you want to measure or to detect something. I told you before, you can look at the spectrum of the probe pulses, so you can look at the spectrum of the radiation transmitted from the sample, but you can also ionize, because it's XUV radiation, you can ionize your sample and you can measure the electrons that are ejected. You can image the electrons that are ejected and learn about their dynamics in the sample, or you can measure the fragments that are originated out of the ionization. So you can do different kind of measurements here. So again, I will show you two approaches that are used in attosecond technology. One is the rabbit and the other is the streaking, where basically you combine this attosecond pulse with the infrared field. You send it to an atom, you ionize it, and you measure the electrons that are photoionized out of this target. Why is it important to measure the electrons, and to learn about photoionization? Well, you know the photoelectric effect as physicists, actually is very well known. Everyone knew it since the Nobel Prize in physics to Einstein, the most famous physicist on earth. But the question is, photoionization instantaneous? Most of the people will respond wrongly, would provide the wrong answer, even physicists. If you're asked, is photoionization instantaneous, so you send a light pulse, you get an electron out, I bet most of you will tell me, yes. Why should there be any delay in the photoemission of an electron? I send my light, the electron is emitted immediately, right? And this is not the case. I said it's a wrong answer, and I know the majority would say that because you have to analyze the problem of photoemission from the quantum mechanical perspective, in which the electron is an electron wave packet. And the electron wave packet that emerges out of, the electron was bound, so it was inside a Coulombic potential. And when the electron wave packet comes out, it is scattering with this Coulombic potential. It's acquiring a phase. Okay, so the electron is a wave now, it's not a particle. It's a wave. And the wave is scattered, and so it's like for you, for some of you who have been studying lasers or laser sources, it's like a chirp. If you want, to your light. In this case, it's the chirp induced to the electron. So if you consider an electron wave packet which is unperturbed, this is the orange wave, but the electron which is ionized instead scatters with the potential, and then you have the blue wave, which is distorted, is chirped, because there is a phase acquired. And the energy derivative of a phase corresponds to a time. So there is a time at which the electron will appear in the continuum, will be photoionized, which depends on this scattering on the potential. How can we measure this? Because this time is extremely short, is in the order of attoseconds, so few hundreds or few tenths of attoseconds. Well, you need different tricks. One is this rabbit technique, which I will not explain because of lack of time. But the other one is the streaking that I want to concentrate for a moment, as also the technique that has been used to characterize the attosecond pulses and say these are really attosecond pulses. Remember, you have a gas target. You send both the pulses, the infrared and the XUV, to your target. You ionize. Now you have an electron wave packet with a certain kinetic energy. And what you do is that this electron wave packet is streaked. We say it is streaked in a sense that it acquires momentum, or which is moving it up and down, as in this figure, according to the external laser field. So we modulate this electron wave packet. So if you measure the kinetic energy of this electron wave packet in time, you get the laser field. This is the laser field. Okay, that's also a beautiful image of a laser field. It's a petahertz laser field that you will never ever be able to measure in other ways, if not with a gating technique like this one, which is showing you the laser field very nicely. But you can also use this figure, and I want just to skip a little bit of the details. You have to analyze this spectrogram, as we call it, to extract the characteristics of the light, of the XUV light, and in particular, for the one of you that are familiar with ultrafast lasers, there is a technique which is called frequency-resolved optical gating that is used to characterize laser pulses, to get the spectral phase of laser pulses. In this case, it's a similar spectrogram, so we also get sort of frequency-resolved optical gating. From which we can extract the phase of the electron wave packet. This phase contains both the chirp, or the phase of the XUV pulse, and the phase that has been acquired in the atomic target, what I told you about the scattering. So there is a term, which is the scattering phase, that we can extract, and from that we can learn what has been the time that it took for the electron to be photoionized. This technique can be then used both to characterize the XUV pulse and to extract the atomic phase. So that was the first streaking measurement ever performed that gave the Nobel Prize to Ferenc Krauss. And you see it's very ugly. I mean, you don't really see an electric field here. You see something, but at that time was not so clear. And in time, much better streaking measurements have been done with retrieval of pulse duration in the order of 100, 150 attoseconds. But then now, as I said, there are even pulses as short as 19 attoseconds. So the technology has evolved a lot. But what I told you about the photoionization time is important because, for instance, if you take an atom and you measure the photoemission from different orbitals, you would expect a difference of time in photoionization because they're scattered from different potentials. And indeed, with this accurate measurement, you can even extract a difference in time in photoionization of about 20 attoseconds. This is an extremely short amount of time. And that's why most of the people would say photoionization is instantaneous, because define instantaneous. Okay, it's enough to be instantaneous in a sense, but you have to be very accurate to see that. Okay, how long do I still have? With the questions, so just to let them ask a lot of questions at the end. Exactly. So these are kind of topics that I'm trying to give you, so to say, different topics that I'm bringing up to guide you a little bit into the technology. So far I said, okay, how we generate these short pulses, how we can use them for chronoscopy approach, which means to time an event, for instance, to time the photoemission event of a photoelectron. And of course, I have many more examples of timing photoemission with streaking or rabbit approaches. If you're interested to know more, just ask me after, reach me out. I can give you whatever sources, literature, and information about it. I don't want to spend too much time in that because I want to use the second part more to focus into the topic of attochemistry, or what we are trying to do with this technology now. Okay, so let me first talk a bit about the light sources, because again, the way we want to do this attochemistry, or the way that we want to image and control the dynamics of electrons in molecules, is based on this pump and probe approach. And here is again the interferometer I showed you before, and this was the way I will show you in a moment, in which we started the investigation of these electron dynamics in complex molecular systems by combining these XUV attosecond pulses. In this case, it's XUV. You see this is a typical photon spectrum, which is extending up to 30, 40 electron volt. Continuous, you see it's a continuous emission. When you see a broadband continuous emission of several tens of electron volts, you know it's an attosecond pulse by now, right? I showed you a broadband, a continuous emission is an attosecond pulse. And then we have an infrared pulse, a few femtosecond infrared pulse, which is combined with that. And what we can do now, we do a pump probe experiment. But as soon as I send my XUV attosecond pulse to the target, I activate this ultrafast electron dynamics. And you will see that in an example soon. But given the high photon energy of the XUV attosecond pulse, what I do is basically ionize the system, right? It's nothing I can do. It's too high photon energy. I will extract an electron. I showed you the photoemission, for instance, as a process that I can study. But you also know that most of the photochemistry or the light-activated chemistry on Earth that is of relevance for many applications, and I said multiple times, light harvesting mechanisms, like producing renewable energy sources and so on and so forth, is based on our solar light, which is penetrating our atmosphere. So solar light, of course, contains also the extreme ultraviolet or X-rays or other X-ray radiation, but this is not penetrating our atmosphere. So all the phenomena that we can study in molecules with extreme ultraviolet light as a trigger are actually more for relevance for astrochemistry, if you want, or everything that is happening above our atmosphere. But on Earth, this radiation would not penetrate. So there are no chemical or biochemical or chemical mechanisms here activated by extreme ultraviolet light or photoionization. Okay, so that's just, as I say, as a general interest, we can study multiple mechanisms activated by photoionization, but this is not what is of interest for photochemistry or for light harvesting. And that's why in my group we have been developing or pushing a lot the laser technology in order to produce instead very short UV pulses to be combined with our attosecond pulses. Now, what we want is that is UV ultraviolet radiation as a wavelength. You remember, short wavelength means short pulses, right? I need a very short wavelength in order to produce short pulses, otherwise I'm limited by the carrier wavelength of my laser. And the ultraviolet is already quite a short wavelength, so it enables the generation of very short pulses. And it's quite of interest because the ultraviolet part of the solar spectrum is activating a manifold of mechanisms on Earth. I mean, from damage, as you know, this is the first thing that you are exposed since you are a kid, because you are told to put your sunscreen when you are exposed to the sunlight, because the DNA in your skin gets damaged by the UV light from the sun. But UV does not only have a detrimental effect. In fact, UV light activates the production of vitamin D in your body, which is essential for your survival, as well as many other chains of biomolecular or molecular mechanisms that are important on Earth. So ultraviolet light is very interesting, and we thought if we can generate UV pulses that are short enough that would not spoil our temporal resolution, then we can still follow electron dynamics in molecular systems, which is not only activated by photoionization, but also by photoexcitation, which means the UV is absorbed, the molecule is excited, but not ionized, and we can mimic some of the mechanisms that are important here on Earth. So we designed and developed new attosecond beamlines for this attochemistry that now are combining either infrared or XUV or XUV and UV. And UV now is becoming more and more I would say, the key player in our experiments. The way we produce ultra-short UV pulses is now not the high-order harmonic generation process that I explained, but it's a third-order harmonic generation. So we are now back to the perturbative regime. But we have developed a unique technology which is based on a glass chip. You see it there on the top. It's actually a laser machine piece of glass in which we create reservoirs. The central reservoir that you see with UV generation is where we inject the gas at very high pressures. And the subsequent reservoirs, in fact, are used for pumping very fast the gas out, such that the gas is confined in the central section of this device at very high pressures. And we generate the third harmonic of our fundamental laser, which is in the ultraviolet, in this high pressure gas. And as we adjust the pressure, we can see that the initial UV radiation emitted, which is this dark blue spectrum, gets broadened a lot. So if we increase a lot the gas pressure, we have nonlinear reshaping effects on the driving field, which enables the broadening of the UV, such that we reach a transfer limit duration, which means the duration, the shortest pulse duration achievable with these light pulses, close to the single femtosecond digit, which for the UV is actually very good pulse duration because it's getting closer to attoseconds. We're not attoseconds, but it's enough to resolve electron dynamics. And we also have other approaches for nowadays in my lab to produce UV radiation. This is based on another mechanism. Again, it's a nonlinear process which is happening in gas. This is a fiber where we send our infrared laser. And then there is a balance in the fiber between nonlinear effects and dispersion, which is leading to a soliton propagation. I don't have the time to dig into that because the lecture is on something else, but if you're interested, I can also explain more on the side. But anyways, this process, which has been introduced by John Travers and co-workers, is able to produce very, very short UV light pulses out of this nonlinear mechanism. And one of the characteristics of this light is that it's tunable. So by adjusting, for instance, the gas pressure in the fiber, you can tune your radiation and explore different wavelength ranges. And these pulses at the moment we produce at very high repetition rates, up to 50 kilohertz with our laser, with high pulse energy up to 1 millijoule, and covering the whole UV visible range, which is relevant for many biochemical mechanisms. These pulses are as short as a few femtoseconds. The shortest we get is still with the chip that I showed you before, which is approaching the single femtosecond digit. But this is, as I said, short enough to look into electron dynamics. Okay, enough for the light sources. I told you it's nice to have these pump and probe schemes, combination of different colors, UV, XUV, infrared, attosecond locking in terms of interferometric stability. What can we do now with molecules? Let's take a step back again. Let's go back to my intro about controlling or looking and controlling at the structural dynamics of molecules and otherwise looking at the electron dynamics. So as I said, structural dynamics has been explored, or the filming or controlling the structural dynamics has been explored quite in depth in the field of femtochemistry. What it's totally unexplored as of now is what can we effectively do by looking or filming the electron dynamics and now getting access to these electron dynamics. What we can start to figure out is, okay, now we have a completely different light source, a different time scale, different frequencies and bandwidth and so on. What happened in the molecular system and which kind of control can we achieve in the two cases that is different? Okay, let me explain what has been done with lasers in terms of control of molecular dynamics and molecular reactivity with femtosecond lasers, so to say the conventional femtosecond lasers. This has been the field of femtochemistry for many, many years, and actually still a very active field, which was resulting in the Nobel Prize in chemistry to Ahmed Zewail, the founder of this field, or the pioneer in this field. And here the idea is the following. I mean, this is the energy landscape, the typical energy landscape of a molecule. As I told you, in a molecule, you have different atomic nuclei. The electrons are the glue. The electrons, they create a force field for the atomic nuclei to be placed in specific positions, right? I mean, there are only a few stable structures for molecules that are enabled by the electrons that creates the bonds. Okay, this configuration, this force field is connected to potential energy surfaces. So these are the potential curves connected to this force field. And this represents electronic states. So if this is the ground state, ground electronic state of your molecule, the molecule typically sits here in the minimum. It's steady, almost steady. Quantum mechanically, we know the molecule is never steady because there is zero energy fluctuation, so it's always in motion. Nothing is really steady, but let's say in first approximation and according to our time scales, it's steady, it's frozen. I come with my laser light, and what happens is that I promote the molecule from the ground state to some excited state. These are electronically excited states. Now, the following dynamics in the excited states will dictate completely what is the outcome of your chemical reaction, whether the molecule will change conformation, the molecule will react with some other reactant, whether the molecule will dissociate and so break in pieces, will be destroyed, or things like that. Okay, so it depends on the evolution along these curves. Those curves, they often have the so-called non-adiabatic crossings, which means that they cross, and this creates a possibility for the molecular wave packet to be initially on this state that I called, in this case, S2, which leads to these photoproducts, instead to go into the other curve and get to other photoproducts, okay? So then you get a different reaction for light harvesting when you want to produce energy for photocatalysis. This is very important, that you want to go one way and not the other way, because you want to lower energy barriers and not enhance energy barriers, right? So somehow you want to be the driver here, and you want to say, well, I want to sit on this curve, or I want to sit on that other curve. I want to decide what's happening, in fact, to this molecule. I want to decide the so-called branching ratios of this reaction. And so what these people came up with, it's a very clever idea. I say, okay, now I tune my femtosecond laser at the color, a precise color that I want. In this case, I target, for instance, the excitation of S2. And if I shape my laser field in the proper way, then I can change the probability of going here or here, depending on how the laser pulse is manipulated within the initial excitation. And that is actually very nice, and in a sense, it has been working in some cases. Most of the cases, the main problem is the dissipation happening in the molecular system. So the molecule is not isolated. It's in a bath of other molecules, water or other solvents around it, and so on and so forth. So there are often dissipation channels that are not allowing to end up exactly where you thought you were going to end up being. And so this is actually something that femtochemistry has been facing in these coherent control schemes for a very long time. Try to exert a control in a coherent way and to beat nature in a sense of getting to more efficient photoproducts and so on, fighting with dissipation effects. Now we are in the attosecond scenario. It's a completely different scenario. Now, if you notice, before I said my pulse, although it's a pulse and so it's not monochromatic, it's relatively narrow band because it's a long pulse. And so I can target a specific energy that I want to reach with my green arrow. You see here I can reach here because it's the central frequency of my pulse, and this is the excitation of S2. So I don't come to S1, I don't come to Sn, but I go to S2. Now I have the broadband attosecond pulse, which is really, really, really broadband. You see now the frequency covers the number of electronic states. They are all eligible for excitation. There is no selectivity, not at all. Okay, I'm not targeting one electronic state. I'm exciting all of them, all together. But I'm exciting them, first of all, instantaneously. So we can really say this is an instantaneous excitation because the pulse is so short that the molecule is not moving at all during the light excitation, right? All the atoms are frozen, nothing happens, the molecule is excited, okay? While if you use a longer pulse, the molecule meantime is moving. You remember there's always a dance of the molecule, and this is on the femtosecond time scale. So if you go too long in time, then you're exciting the molecule in different nuclear positions, right? And go back to this blurred image that I told you before. Everything is blurred by the dynamics. Here, everything is frozen, and so I know very well what I'm exciting because the pulse is very short, the geometry is frozen, and I excite a so-called coherent superposition of electronic states, which is very different from before, because as I excite this coherent superposition, I create a so-called quantum coherence, which means that these electronic states are adding up coherently with a certain relative phase, and my electron wave packet will be modulated by this with this interference between the states, and this will create a non-stationary density distribution. So the electrons will move around. The glue that is keeping the molecule together starts to move. It's not such an effective glue anymore. And this means that at this time of the excitation, I'm affecting the force field. I'm affecting the force field. So classically, you will take a ball, you launch it down from this curve, and you will get always the ball going out here or whatever. Quantum mechanically, you don't know where you end up being, first of all. And since you are launching simultaneously all these states and you are affecting the shapes of these curves because you change the force field, you can get completely different outcomes. So the idea is really, how can we shape this interaction? How can we interact with the molecule such that we can really affect the chemical reactivity because we are changing completely the landscape of the molecule, okay? Redefining chemical bonding, redefining the chemical forces, and all of that. So we are still at an open question, and at the end of my lecture, you will not say, wow, we can really do it. No, we can't. At the moment, we don't do it yet. So we are only learning, understanding, and we are trying to manipulate the system in a way that we get different outcomes, but not yet really at the stage that we can conclude this is really possible. What can we do is certainly we started to trace these non-stationary charge density distributions, so the fact that the electron density moves very fast. What we can trace is the so-called charge migration mechanisms, which is at the basis of what I explained to you just a minute ago. Here, the idea is that when you suddenly, actually the process was at first only theoretically predicted for sudden ionization of the molecular system. So you take your molecule and you ionize it with your attosecond pulse, which is, as I said, a sudden interaction with matter. If you ionize it, then what happens is that, as I said, there is a coherent superposition of electronic states, there is an interference, and therefore this density is changing in time. And here you see a simulation where you have a small peptide, for instance. This is the residual charge density distribution in the peptide after the interaction with the attosecond pulse. And the charge is not staying there, it's just moving. It's distributing along the molecular backbone, and it's going at the end of the other, on the other side of the molecular backbone. In this case, within a few femtoseconds, but it could be also within a few attoseconds or whatever. It depends only on the energy of the electronic states into play. So that's already nice, because here you can see, okay, via the charge migration mechanism, indeed, there is a way to, as I said, change the chemical bonding in a sense, because you are affecting the charge density distributions. And the first thing that you want to see is whether you can really film this process. So how can we create this charge migration? And this is like very scary, because it's a formula that I'm showing here, so some math that maybe you don't want to deal with. But it's just to say, when there is photoionization of a molecular system, and this is the molecular wave function, you can create a superposition of electronic states in two ways. One is the coherent superposition of the valence states that have been ionized by your attosecond pulse. Valence ionization is, in this cartoon, an electron kicked out from the outer states. And if you ionize many of those states, as you will see in a second, you activate this charge migration. Another way of ionizing the system is that if you increase the photon energy, you start ionizing from the core states, not the valence states. And these core states are particularly active. They're not, so to say, they tend to be very interactive with the other electronic states, because here electronic correlations are playing a major role. And several mechanisms can happen after a core ionization. For instance, one is the so-called Auger-Meitner decay, in which another electron is filling this vacancy, and the excess of energy is seized to a second electron, which is now ionized. So you don't only have the primary ionization, you have a secondary event of ionization, which is actually due to the Auger-Meitner decay. So we say this is a two holes, one particle state, which is a coherent superposition as well of electronic states. So going back to our attosecond pulse, if you take a molecule like the molecule we picked, which is very complicated at that time for the experiments, phenylalanine is an amino acid, and you take the broad bandwidth of your attosecond pulse, you can see here all the possible electronic states that we are ionizing from. So what I told you before, the broad bandwidth means ionization, coherent ionization from a lot of electronic states. And this is actually activating the charge migration. And this is what we did in terms of experiments. So you have your molecule. As I said, we picked a very complicated molecule at that time. We thought, yes, aromatic amino acids are interesting because they are the nano-sized antenna of our proteins. They capture very efficiently the UV, VUV light, and they dynamics, electron dynamics, this charge migration must certainly happens here. We're a bit naive because this molecule is complicated, the electronic structure is very complicated, and therefore this dynamics is also very complicated. Far away from what I showed you before, like this linear motion of charge, very nicely depicted in theory. It's a chaos. So here you have your attosecond pulse, which is ionizing and creating a coherent superposition of a manifold of electronic states that I showed you before, like really tens of electronic states. And then we send our few femtosecond probe pulse, infrared probe pulse, to probe the dynamics that have been initiated by the attosecond pump pulse. And we do that, at that time, we did it by not looking at the photoelectrons directly, but by looking at the fragments that are produced out of the dissociation of the molecule, so the ions that are produced here, as a function of the delay between the two pulses. So you will measure a mass spectrum, and you measure it as a function of the delay between the two pulses. And we did it both for phenylalanine and tryptophan, both aromatic amino acids. A lot of fragmentation is in the mass spectrum because as you ionize with XUV photons, as I said before, you destroy the molecule, you break it in many pieces. In that case, we observed a very interesting dynamics in a fragment that is basically almost non-visible in this mass spectrum. It's the doubly charged ammonium ion, which results from the loss of this carboxylic group here. By measuring the yield, so the mass of this fragment as a function of the delay between the two pulses, we could observe very fast modulation, very fast oscillations of the yield. And this was already a very interesting and surprising observation because we were saying, why is the yield of this fragment modulated at these time scales? It cannot be a structural dynamics because there is even the fastest vibrations in this molecule are in the order of 10 femtoseconds, so cannot be that fast. So it must be related to the electron dynamics. And before coming to the point that we understood which kind of charge migration was happening there, we had to collaborate intensively with our theory collaborators that were calculating this initial excitation that I showed you, this coherent superposition of electronic states. And they came up with these very nice movies in which you see the charge dynamics. Purple means an increase of charge, yellow a decrease of charge, so the charge is moving away from some places and is moving into other places. And here, the interesting thing is that it's chaotic. I mean, in a sense that you will look at this movie, it's not like a nice charge dynamics, as I showed you before. They would say it's really, really complicated what we are activating here. But why can we now see very clear oscillations despite this very difficult or complicated dynamics going on? And this is because our probe pulse was, later on, we deduced that the IR probe pulse is primarily absorbed by the amino group containing the nitrogen in the molecule because the cross-section there is higher for absorption. And therefore, we are very sensitive on the charge variation on that side, both for this amino acid and the other. And we see these yellow-purple variations that results in the change of the fragmentation rate. Nowadays, we are becoming smarter and we do better experiments. I just want to mention that attosecond pulses are not only available at our tabletop sources, but also now at free electron lasers. I don't, of course, explain you the technology here, but if you're interested, of course, reach out. There are attosecond pulses produced here in the X-rays. And why X-ray are interesting? Because now we can do a similar experiment. So we ionize the molecule with the first attosecond pulse, and we probe it with the second attosecond X-ray pulse, which now can target specific atomic species, because in the X-rays we can really target the absorption from the nitrogen, from the oxygen. And we now see, these are preliminary results for phenylalanine and tryptophan, but that if we go to the oxygen or the nitrogen edge, we can identify oscillations that are very similar to what we have been measuring in the past with our tabletop source, but now knowing where we are looking exactly with the X-ray pulses. Do I have still a few minutes, or minus? My bad, yes. No, but then, okay. I want just to then conclude by saying that I had another example to show, but I don't have time to do that. That we have been moving to the use of UV pulses.
No, please tell about the bottom picture. That's interesting.
I had a very nice example to say here about chirality. Yeah, then I say a few words about it. I'm allowed by the chair. Yeah, among the various molecules we are studying, we are developing a lot of interest into chiral molecules. Chirality, as you say here, it's a very important property of matter, which is exploited both in condensed matter systems and molecules. These are mirror images, one of the other, like exactly as our ends. And in molecules, it's particularly interesting because molecules, despite having the same chemical formula, they have a very different chemical functionality, depending whether they are one enantiomer, the right one, or the left one, okay? And this is because we are homochiral, so in our body we only have one chirality of molecules, and we need to interact with the molecule we take as drugs. With the end shaking. If it's the end shaking is done with the wrong end, it doesn't work, and it's very toxic. So something that is like a very, it has an healing effect, like L-methamphetamine, which is the nasal decongestant, is instead a poison in another enantiomeric form. Well, somebody says it's not really a poison, I can have fun with it, but for your body is a poison. And so what we have been doing, that I think it's the interesting point here, is that what happens to this end shaking, to the chirality of molecules when we excite charge migration, when we activate these ultrafast electron dynamics? And here I can only, as a spoiler, say, because my time is over, but with our very short UV pulses that I introduced, we activate the charge migration in the molecule, and we can make the molecule, and this is just this figure here that I want to show you. This is the charge migration which is activated in the molecule, the blue-red bubbles you see there. This charge migration, we measure, we had a way to measure the end shaking, the chiral response of the molecule as this charge migration is happening in time. And we see that we are actually end shaking with the left molecule and with the right molecule in time. So to say we are changing from left to right. Although the molecule is the same, it's only the right molecule. We're not changing the molecule itself, the structure, but the fact that we activate these electron dynamics allow us to make the right molecule behave as the left molecule in certain instance of time. So our goal is a little bit to use this as a control scheme to, as I said, manipulate the chemical response of molecule by activating these electron dynamics. I have no time, so of course you are welcome to ask me afterwards all the details about that. And thank you very much. Well, I said, I mean, light conversion needs to be there, so I have to.
Thank you, Francesca, for this very interesting, if a little bit chaotic lecture, but yeah, it matches the subject of your study perfectly. I'm sure we have some questions, so let's ask. And
thank you for a very interesting presentation, a lot of knowledge. I was wondering, so you can track electrons and all these transitions. could these spectroscopic measurements be done for some like DNA molecules or something like that?
Yeah.
I don't know if they're larger or smaller. I'm not from biology
Yeah,
side.
So we are working at the moment with subunits. So we have been measuring also charge migration, for instance, in DNA subunits. In adenine, we observed the charge inflation mechanism that we have been using to prevent the photodissociation of the molecule. So it's a sort of a photoprotection mechanism. Although I must say these DNA subunits are in the gas phase as we study them in the gas phase at the moment. And this is not representative of the DNA environment, which is instead a macromolecule with additionally solvation in our body. And so for that, I don't think we will go to the point of studying DNA itself, but we are studying nucleosides at the moment, which are solvated in water via different approaches, so not photoionization because you cannot detect charges out of the liquid, but for instance, by looking at the absorption of light, as I explained at the beginning, as another approach of time-resolved measurements. And we are learning some interesting aspects of this ultra-fast charge dynamics as you increase the complexity and as you embed the molecule in a solvated environment.
Thank you.
Okay. Other questions? Don't be shy. Yeah, Andrus.
Thank you for interesting talk. So my question is somewhat philosophical.
Yeah.
So you showed very nice techniques to probe signal in time, and then you use a lot of sophisticated approaches to model what happened. I wonder if you have some thoughts. Is it also possible to image what is happening? So do you foresee some techniques which allow to see actually the electron and resolve it in space?
Yes, thank you for the question, because it's actually what we want to do next. I was awarded an ERC grant recently exactly to do that. It's a synergy grant, so that will be in cooperation with a team that is using X-rays to do diffractive imaging. So this is an imaging approach, or if you want a microscope in a sense, because you want to look directly into matter. And the idea there is more to move these kind of measurements from the tabletop sources to the, I showed you attosecond X-ray sources at free electron lasers. And we could excite the dynamics in the molecule using an external laser pulse, and then use X-rays with very high photon energy to get into the quantum crystallography regime, where you can really get the scattering from the electrons. Okay, so you don't resolve only the molecular structure, but you resolve the charge density distribution. It's a very tricky thing because in every imaging approach with X-rays, you have a certain diffraction pattern, and you have to go back to the real space, to the object. And for that, you need to solve a phase problem, a phase inversion problem, because you measure only intensities and you want to retrieve the object. So the missing phase information can be, in principle, recovered with algorithms that can be supported also with spectroscopic quantities. So combining like the tabletop spectroscopic quantities that I've shown with the diffractive imaging approach. And there should give you like the direct charge density distribution in time.
Thank you.
Okay. Another question here.
Okay, thanks. Thank you for the presentation. My question is, since the charge movement is in femtosecond scale, do you record it in terahertz spectrum, or do you use this technique? Is it possible to use it?
So the charge dynamics is either in few femtoseconds or even in attoseconds sometimes, and terahertz pulses, they don't provide the resolution because the terahertz wave is a much longer time scale, it's normally more the picosecond, I would say. And what I would say, it depends what you want to record, right? What are we recording? Are we recording A spectral, yes, but it depends, because if you want to have, like what I showed, is photoionization. So you need to ionize the system to extract the electron. And so you cannot, you need to use this high photon energy to ionize the system and get your observable. Can be a fragment, can be the electron. No, I mean, I really take out, my electron is moving and I take it out and I look at it, okay? So I need enough photon energy. So it's not only a matter of time resolution, but it's also a matter of photon energy, which is needed to photoionize the system. And terahertz doesn't have this photon energy. If you look into the, as I said, into the absorption of light through a sample, of course, you can do it also with terahertz, but there we are dealing with energy scales that are more on these milli-electron volt energy scales, which is very relevant, for instance, for condensed matter, or in general for structural dynamics. So it could be phonons, vibrations, or other things that indeed are happening on those time energy scales of the terahertz radiation. So terahertz radiation is extremely useful, but for this class of structural dynamics that happen in matter, which are far away in the energy range compared to the energy range that I discussed today.
Okay, we have cut into our break enough, so let's ask the questions during the break, and let's keep it informal. Thank you, Francesca, again.
Thank you.